last class we have started the discussion on programmable logic devices. So far we have read the what do we mean by programmable logic devices and the different configurations. Now we will continue this class the same thing, the programmable logic device. But before that, quickly we see the last class, the quiz questions of the last lecture. So, first question was, what is programmable logic device? Name its different configurations. So, programmable logic devices, we have seen that it is mainly of some array type of structures that can be divided into two parts. One is called the left hand side is AND array, right hand side is OR array, and the either one or both can be programmable to implement or to realize a logic device. This is called the programmable logic device. And name its different configurations. We have read the configurations. First one is programmable ROM. So, if we read the question, the question quiz 2 or this is question 1 B. B, that different configurations are one, the PROM, programmable read only memory. Second is programmable array logic, PAL. Third is programmable logic array, PLA. Fourth is complex programmable logic devices or CPLD, and fifth is field programmable gate array or FPGA. So, these are the 5 configurations we have read. There some more can be there in the literature, but they are most of the cases they are part of or some variety of one of these configurations. Now, quiz 2 was, what is the difference between a PROM and a PAL, and 3, what is the difference between PLA and a PAL. So, again quiz 2 answer is the difference between PROM and PAL. So, PROM we have seen that answer the programmable ROM has fixed AND array and that has implemented by a into two to the power n decoder and a programmable OR array. Programmable OR array. So, here the main thing is it has a fixed AND array and a programmable OR array, whereas the PAL, it is totally different, reverse, or we can tell that it is reverse, that PAL has, or programmable array logic has a programmable AND array, programmable AND array and a fixed OR array. So, this we can tell this is a totally reverse thing on the, if we consider the programmability. Now, question 3 was the quiz 3, it was the difference between PAL and PLA. So, already we have seen PAL has a programmable AND array and a fixed OR array. So, these will be as it is, it will be coming as PAL, and PLA has both the AND array and OR array programmable. Array programmable. So, it is more flexible, both the AND array and the programmable. So, it is more flexible. So, these are the answers of the last lecture's quiz question. So, now we continue the discussion on programmable logic devices. So, where we have seen in details, or we have read the details of PROM. Now, we see that the actual architecture and the design of the PAL, the programmable array logic. Just now we have seen the PAL has a programmable set of ANDs combined with a fixed ORs. That means AND array is programmable, OR array is fixed. Now, what is the disadvantage? See, ROM guaranteed to implement any M functions of n inputs, because it has a fixed AND array and we have implemented that thing by a decoder. So, all for a n variable or n input variable functions, all 2 to the power n minterms are available in the output of the AND function, AND array. And for this M output means M different functions are there. So, for the M functions, any set of the 2 to the power n minterms, that means all minterms are available, all 2 to the power n is the all possible minterms for n input variable. So, ROM guaranteed that thing, PROM, but PAL may have too few inputs to the OR gates, because PAL has a programmable set of ANDs combined with fixed ORs. So, the advantage is that it may not realize the all possible functions that are available or possible for M output, N input programmable logic devices. So, it has some restriction. Now, what are the advantage? So, for given internal complexity, a PAL can have larger N and M, because it has AND fixed or fixed and programmable. So, it can handle that larger input variables, and as well as or fixed. So, as it is a fixed, so in the design itself, as it is a fixed OR plane, so that M can be initially itself, that M can be, the larger value can be selected. Some pairs have outputs that can be complemented adding POS functions. So, this is a very important property. See that some PAL functions that are output functions that are complemented. So, here we get a again some more minterms using this. Now, no multi-level circuit implementations in ROM without external connections from output to input, but as here the PAL has fixed OR. So, as if some more additional circuits, if we add to the fixed OR plane, then we will be getting the more, we have the more choices. PAL has outputs from OR terms as internal inputs to all AND terms, making implementation of multi-level circuits easier. So, here it is possible to get the multi-level circuits, and if we take, it is a programmable AND though, but we can take worst case or exhaustive case all possible minterms, and then implementation of multi-level circuits are easier by using PAL. But normally in PROM this type of connections cannot be done, because here it is a fixed AND and only programmable OR. Now, we take one PAL example. So, it has a programmable AND plane. So, this is the AND plane. This is my AND plane. See, it has 3 inputs and we have taken this A and A complement, both are available. So, this line is A and this is my A complement. Similarly, this is B, this is B complement, this is C, this is C complement. Now, it has fixed OR gate OR plane. So, we see it has fixed OR plane. See, this is the fixed OR plane, and what is there? So, in the AND plane realizes the min terms. As it is a programmable, some of the min terms are as needed or as required, that are synthesized. And then these are the inputs of AND gate, and see these are then realized by, these are the OR. So, actually the fixed OR we should give the fixed OR plane as the these two input OR gate. So, see here there are cross are here. So, that means this is A, this is A and cross is here. So, this is a B and this is C bar. So, that means the output of this AND gate output of this AND gate is A, B, C bar. Now, similarly, the second line realizes, say this cross point means A bar, this is B because B line is here, and this is C line. So, this is A bar, B, C. So, the output of second AND gate is A bar, B, C. Then these are the two inputs of the first OR. This is my first OR gate. So, this is A, B, C bar. So, this is nothing but F1 is A, B, C bar plus A bar, B, C. Similarly, the F2 realizes the OR of, that means sum of two, the output of two AND gates. See the first one, the first input of the first AND gate is, this is A bar and this is B bar. So, first one is A bar, B bar. Now, second input of the OR gate is A, B and this is C. So, this is A, B, C. Now, see here this is a fixed OR plane. So, that is why the two output functions that are already, always it should be coming from the, this is a fixed, that means it has two input OR gate. So, if we need a 3 input or many of the, this is not a variable. If I want 3 input, it is not possible from this structure. If we want more than 2 input OR gate, that means 2 input OR gates means more than 2 input OR gates means if the number of minterms in the function f is more than 2, then it is not possible to realize by this PAL structure. So, this is a restriction of PAL. It is a fixed, that means here it is always, it is already defined, already pre-designed that my output function is the sum of 2 minterms only. But the minterms can be consist of any of the literals restriction. Now, some more advantage is also there for this fixed OR gate or plane. See, earlier it was only combinational. Now, we can realize the sequential logic also by using a PAL structure. As this output plane, normally OR plane we call the output plane because the output function is can be computed or is taken from the OR plane. So, in the output of the OR or the PAL plane, PAL, we can add some D flip flop. So, if we see this example, see again we are taking the 3 input. So, this is my AND and the 3 input variable. So, this is A bar, B bar, C bar, and the output of the 2 AND gate, this is A B C bar, this is A B C bar, and this one is A bar B C, this is A bar B C. So, this output, it is latched to this by this D flip flop, which is attached here. So, when the clock is on or clock is 1, so here we are applying 1 clock. So, when it is 1, clock is 1, this is latched to this D flip flop, and the circuitry here, one circuitry we have taken, that one multiplexer enable, that means when we need it is as if this is stored and the F1 circuitry is we are getting. Another thing is, if I add a inverter here, see this is one inverter. So, the function, if it is enabled, we are getting F1 and the function can be taken as the complemented of that thing, F1 as well as F1 complement is also possible. So, adding a D flip flop or more than one flip flops depending on the circuit complexity, what we can do? We can realize the sequential circuits also by using the PAL logic. So, this is one good advantage over the PROM. So, here if we see one example of another PAL example, that how we can realize this thing. Say PAL with 4 input and 3 output with fixed 3 input odd terms, and output equations, there are 4 output equations. F1 is A dash B dash plus C dash, F2 is A dash B C dash plus AC plus AB dash, F3 is AD plus BD, actually AD plus BD plus A dash B dash plus C dash. So, first we realize F1 F2 and then we will be seeing that F3 F4. Actually this is one special type of functions where the 2 output functions consists of other 2 output functions. See, F3 consists F1 also. A dash B dash plus C dash is nothing but F1. This is F1. Similarly, F4 consists F1 dash, because see if it is A dash B dash plus C dash dash. So, this is F1 dash. Now, we see that how we can realize this thing. So, first we write A dash B dash plus C dash and A dash B C dash AC plus AB dash. C dash AC plus AB dash, and F1 is A dash B dash plus C dash. So, first we, how many there are 3 inputs here, ABC. So, if we draw the programmable or AND plane, so these are, there will be 6, because 6 signal lines, because this is for A, this is A dash, this is B, B dash and C, C dash. So, this is A dash B dash plus C dash. So, one cross will be here, one cross will be here B dash. So, this is, if I put one and get, this is A dash B dash. Similarly, it is only C dash. So, here only this is C dash. Now, we give a OR and it will realize the F1, it will realize the F1 circuitry. Similarly, if it is F2, we are seeing that there are 3. So, that means this OR gate must have 3 inputs, must have and this will be A dash B C dash. So, this is A dash B C dash AC. So, this is A, this is C AC and then A B dash. So, this is my F2. Now, what we see that the F3 is actually AD plus BD plus A dash B dash plus C dash. A dash B dash plus C dash is nothing but F1. So, this is F3 is AD plus BD plus F1. So, now what we can do, if we take some feedback type of thing, see again from F1 can be a input line. So, if we draw again, then actually earlier we have 3 input variables, 3 input variables. From there we have realized F1, we have realized F1. Now, say if this F1 is fed and it is taken as another. So, this is my A dash, B dash, C dash and this is my F1, and similarly I can add a inverter and this is my F1 dash. So, now F2 was realized, F3 is AD plus BD. So, F3 I can realize how F3 is AD. So, AD plus BD. So, I need another input D and D complement. So, this is my D, this is D complement. So, this is my AD. Another is BD. So, this is D, this is B. So, these two are, this is 2 AND gate, this is AD, this is BD. Now, AD plus BD plus F1. So, I need another, this is, as now here F1 is also a, F1 becomes an input line. I have taken the output of the first OR gate, that is the function F1, as the input of the one of the input variable. That means, it is fed back to the programmable AND plane. So, one output of the fixed OR plane is taken or is fed back to the AND plane as the input variable. So, this is my F1. So, now this becomes my F1. So, now if I give a OR gate here, the F3 will be AD plus BD plus F1, which is actually AD plus BD plus A dash B dash plus C dash. Similarly, F3 is nothing but the some function plus F1 dash. In that case, I will be taking one another line, which is taken that F1 dash as the input. So, this is my F1 dash. This is F1 dash. So, here one advantage we have seen, or one special type of PAL structure, where actually the sum of the output of the fixed OR plane is again fed, they are fed to the input of the programmable AND plane, and in that way it actually extends the or increases the programmability as well as the design variety of the PLDs. So, we can realize F1, F2, F3, F4 by using 4 input variable ABCD as well as the F1 is as the one of the output function, F1 as the F1 and F1 complement as the input variable. So, here the number of inputs are, the input variables are A, B, C, D and F1. So, that means for A bar, for B there are 2 lines B bar, for C bar, for D bar, and for F1 complement, and actually they are coming from the this is the output. So, 5 input, though in the function it is a 5 input variables, but actually from outside only 4 input variables are there. So, in this way the design is compact also. From outside there are 4 input variables, and one variable or one input is actually coming from the design itself, which is another output of that particular design. So, So, this is just now the structure I have drawn, and see, this is actually the A complement, B complement, C complement, D complement, and F1 complement. So, this is that F1 and F1 complement. This is my F1. So, these are the two feedback lines. This is F1, this is F1 complement, and rest of the things are same. This is F2, F3, this is F4, where in F3, F1 is one of the inputs, and in F4, F1 bar is one of the inputs. These are the design of the previous functions. So, the PAL structure and the compactness or the flexibility of PAL to realize the sequential circuits, as well as the reuse the some of the functions already realized to get a new functions, that facility we have seen in PAL logic. Now, we see that programmable logic array or the PLA, and as I already mentioned, PLA has the is the most the programmable features of PLA is the maximum. So, it because it has the two planes, both the planes are programmable. See here the AND plane, this is my AND plane, this is also programmable, and this is my OR plane, that is also programmable. Now, what are the advantages? So, PLA can have large N and M, permitting implementation of equations that are impractical for a ROM because of the number of inputs N required. So, here we have seen that for ROM, that particularly as it is a for ROM it is a fixed AND array. So, we have implemented by using that is by a decoder, and a large decoder means it will take a large area, it will be impractical. Whereas, now actually in real life, here the problem is that in real life often we do not need all of the 2 to the power n min terms. So, if you remember that the PROM, if you remember that in PROM that this is a fixed AND array, it has, say it has n inputs and all 2 to the power n. So, this output means actually these are here all 2 to the power n min terms can be realized, and then it is fed to the OR plane. This is programmable. Now, see here it is n can be very large. See, if n is large, but number of min terms to realize the functions are not so large, they are small, they are few or very few. See, in this case, as n is large, so we need a, this is actually a decoder, a n to 2n decoder, and as n is large, so we need a large decoder, but here only the min terms are very few. So, this is a wastage, area would be very big, design, this is a, the predefined structure of the decoder is very large, but actually I have to realize say only very few min terms. So, this is a very impractical in real life situation. Whereas, this is a, in this PLA, this can be a very compact thing, that even n is large, we need only 2n lines, because both the literals and its complement. So, if I have n variable, then 2n number of actually signals for the n number of variables and its complements, that many lines are needed, but it can realize very efficiently that if the min terms are very less. So, if n is large, but the min terms are very less, then actually the PLA is a very efficient structure rather than PROM. Now, a PLA has all of its product terms connectable to all outputs, overcoming the problem of the limited inputs to the PAL ORs. See that same min term, a PLA has all of its product terms connectable to all outputs. So, same min term can be used by more than one functions. This is the advantage. Some PLAs have outputs that can be complemented. In this case, now in some special type of design, that outputs can be complemented also. Now, what are the disadvantage? So, often the product term count limits the application of a PLA. If the product terms are big, or it is very large number of product terms are needed, then it limits the application. Now, two-level multiple output optimization reduces the number of product terms in an implementation, helping to fit into a PLA, but it has some number of improved or refinement is there using the PLA design, and this problem can be overcome. Another thing we can do, we call the PLA minimization. So, in the first iteration, it may happen that a number of product terms are large, and or that type of situation what just now I mentioned for PROM, that if n is number of input variables are very large, but the few product terms are actually used, then in that case the size of PLA that can be reduced also. So, this is the PLA minimization is called. Now, we see one example. See, the PLA has both the AND plane and OR plane programmable. So, this is my AND plane. and this is the odd plane. And both are programmable. So, both are programmable. So, it has 3 inputs A, B, C, and just like what we have seen that both A and A bar are available. That means, this is my A and this is A complement, B, B complement, C, C complement, and that are given. We can write here also, this is C, C bar, B, B bar, A, A bar. Now, as the cross points are here, so the first, normally we call these are the product lines. So, the rows are called, the rows are product lines because they realizes the mean terms, which is nothing but the product of the literals or the variables. So, these are rows are product lines. So, the first product line or the first row realizes B and A means AB. So, the first one is the AB. Similarly, the second one is C B. So, this is my second product term is BC. Third, similarly, third product term is C B bar, C A, sorry, this is AC, and fourth product term is AC, and similarly the fourth product term is B bar A bar, means A bar B bar. Okay. So, AB, BC, AC, A bar, B bar, these are my 4 product terms. Now, in this particular example, we are seeing that this is my OR plane. This is my OR plane, and actually the P1 terms as if the product lines are the input here. So, it has 4 inputs. The inputs are P1, AB is P1, P2, P3 and P4. Now, what are the, for F1, see this is my P1 means AB, BC, AC, P1, P2, P3, all 3 are the inputs of the OR. So, my F1 is F1 is see AB plus BC plus AC. Now, we are assuming AB plus BC plus AC. We are assuming the other, this is actually here F1 I am considering the OR gate, output of the first OR gate. And if I assume my F2 is here, then my F2 is the sum of two mean product terms P1 and P4. So, P1 plus P4 and P1 plus P4 is AB plus A bar B bar. So, these are the two functions F1 and F2. Now, some more modifications I can do here. See, what we have done in the OR plane, this is some extension or some refinement of the PLA structure. We can add some XOR and other input can be a 0 or 1. So, if we see in details that structure, see what we have done. Now, the as if the one we are considering, the output of this OR gate is a F1 and that we fed to the one of the input of my XOR. Other input can be 0 or 1. Now, if we remember the two input XOR, see if A and B are the inputs of a two input XOR, then the function will be AB bar plus A bar B. So, here if it is F1 and 0 is in this line F1 0. So, that means as if this is my say F1, say this as if this is my A and this is my A and this is my B. Then it should be A B bar plus A bar B. A B bar means F1, B bar means 1, 0 bar means 1 plus A bar means F1 bar and B means 0. So, this becomes F1. So, that means if it is a 0, then as it is F1 will be. So, my XOR input, if the other XOR input is the 0, then as it is I will be getting F1 here. Now, if it is 1, then we see if it is F1 and if it is 1, that means this is my A, this is my B and then AB bar, then F1, B bar means 0 plus A bar means F1 bar and B means 1. So, this becomes F1 bar. So, if it is 1 XOR is 1, I will be getting a F1 bar. So, in this way I can get a complement of the output function by, actually this is another programmability we have added here. Just feeding a 0 or 1. So, this can be again a control line. If it is 0, as it is, I will be getting the function of what actually I want or the output of the OR gate, and if I want the complement, then my control line is 1, then I will be getting a complement of the output. So, here that OR plane gives me that these functions, that f1 and f1 or f1 complement, and here f2 or f2 complement. So, this is my PLA design. The PLA design for a particular next day we will be discussing that how the general structure of a PLA, that means for n input m output equations, how the PLA can be designed. So, we will continue this discussion in the next lecture. Thank you. In the last class, we have read the design of programmable logic array. We have seen that how one PLA can be designed for a set of output functions. Now, today we will continue the discussion on the programmable logic devices. First, we will see that how the what will be the general structure of a PLA design. So, if we consider the one n input m output PLA, then what will be the programmable AND array and the OR array structure. So, first we will consider the programmable AND array. As it is a n input, so there will be